Okay, today is 9/29. Deceleration, what does it mean? You know there's a trap here and you're all being very careful. It's understandable. Okay, that's exactly the answer that I was hoping for. Okay, the way we commonly use it is that to decelerate means to slow down. And you can go on continuing to use it in common everyday language that way. What we want to be careful about in physics is we get, so we use it commonly to mean slowing down. But yesterday we looked at this graph and we said, okay, this is a velocity time graph. In this interval, hey, the slope of the line is positive. It's speeding up. Well, both of those things are true. I need to lip read better. Both of those things are true, but the fact that the slope of the line is positive isn't why it's speeding up. Where is zero acceleration or zero velocity? It's there. Where is crazy high velocity? It's there. The reason we look at this graph and know that that's speeding up is because the value on the y-axis here is larger than here. The magnitude of the velocity is increasing. You are going from 0 meters per second to, I don't know what you're doing there, 10 meters per second. You're physically moving faster. Okay, that's easy. We're in our favorite quadrant of the Cartesian coordinate system here. We're in the quadrant where everything makes sense to us intuitively, and we don't have to think too hard, and we like to not think too hard. So let's stay here for a moment, and then we're going to screw it all up and make you go, whoa. Okay, so here we said slope of the line is flat. Velocity, is the velocity here 0? No, velocity is not 0. Look at where you are. The velocity isn't 0, but the acceleration is 0. You've set up the cruise control. You're moving at a constant speed. From C to D, tell me what's happening to the object.
Its velocity is decreasing.
Okay, its velocity is decreasing because at C we have a larger magnitude for the value of velocity than we do at D. We're going from 10 meters per second and maybe we're creeping along at 1 meter per second. What is the acceleration here, positive or negative? Negative. And how can you tell? Well, give that in more mathematical language. Slope of the line is negative. Okay. So the slope of the line is negative. We would say then that the acceleration is negative, and we would say that the object is slowing down because the magnitude of the velocity is decreasing. Okay. And then, I mean, this is really more of the same. You know, there we have a flat slope. The acceleration is 0, but the velocity is constant. Okay, that's not too hard. Seem reasonable? Seem fairly intuitive. Okay, get your seatbelts buckled? It's not that bad. It's not that bad, if I can pull it up. Now, let's look at this one. And I'm going to expand this as much as I can. First part of this graph looks pretty similar to what we had before. So from A to B, for instance, this is a velocity time graph. Now we have 2 quadrants here, you notice, and that's where we have to be really careful. Acceleration, positive or negative? Positive. Object speeding up or slowing down? Speeding up, because the magnitude of the velocity is increasing. And, you know, B to C, cruise control is set. Acceleration is equal to? 0. Magnitude of the velocity is not changing. C to D, what's happening? So, okay, 2 questions, sorry. Acceleration, positive or negative? Negative. Object speeding up or slowing down? Slowing down. Magnitude of the velocity is getting closer to 0. This is good. So now we're going, oh, okay, so we don't use decelerate. That's not scientific enough. We say negative acceleration. Okay, fine, I'll try that out on my friends in the car. Ha ha, won't I be cool? And that would be great. Except we just can't leave anything well enough alone in physics. So let's now take a look at here to here. Point whatever to point F. First question, is the acceleration positive or negative? Confer with a friend. Come to your answer and see if they're thinking the same thing. And explain to them why if you think they're full of it. That's the best answer I've heard. Okay. Who says acceleration is positive? Okay. Who says acceleration is negative? Okay. Other than because you think it's a trick question and Moser likes to lay leg hold traps out scattered throughout the notes, why would you say it's positive? So anytime an object is moving, it has positive acceleration? Mr. Cruise Control on the highway? Okay. I think he just rescinded his answer. That's good. We're allowed to rescind. Why is it positive? Oh, now that's an interesting way to phrase it. I like that. Okay. I'll give this part away. It is negative acceleration. What gives you the acceleration on this graph? Slope. What's the sign of the slope from E to F? Negative. That's a negative slope. Therefore, the acceleration is termed negative. Is that object speeding up or slowing down? It's speeding up. How do you know it's speeding up?
The numbers are increasing, it's just going the opposite direction.
The magnitude of the velocity is increasing. Here is zero velocity. Here is, 100 meters per second in the positive direction. Well, this is 100 meters per second in the negative direction. Whatever you called zero on your arbitrary number line, this at this point, object is going in a negative direction. It's still speeding up, but it has negative acceleration. It's not actually that bad. If you just remember that the slope gives you the acceleration, tells you whether it's positive or negative, that's really easy. You're all really good at that. You can all look at a line and immediately say slope is positive or negative. If you remember that the change in the magnitude of the velocity is what tells you if it's speeding up or slowing down, this is pretty easy. Okay? Good? 0 to 5? Excellent. Nobody freaked out. 4? Okay. 4s are fine. Hiding under the desk is not good. Constant acceleration. What's acceleration? Sort of in a nutshell. What?
Velocity over time.
Okay, it's velocity over time, mathematically, and just sort of in common parlance, it's the change in how fast you're going and how long it takes you to make that change. We like things constant because they're much easier to calculate. So for our purposes here, we're going to talk about constant rates of acceleration. So your velocity changing, or an object's velocity changing, at a very, very constant rate. This doesn't happen a lot in reality. If you, put the pedal, hit the pedal in your car out on Route 7, between, changes in terrain, changes in your ankle, changes in whatever, even if you think you're holding it pretty steady, there are going to be some pauses. You're going to shift. If you're in a stick shift, you may have zero acceleration for a moment as you shift. If you're in an automatic, there's still a little hiccup point. How many of you can feel when a transmission shifts? Okay, that's a hiccup in your acceleration. Your acceleration rate changes for a moment. We're going to talk about constant acceleration here, and what we're going to do is we're going to build what I call the 4 golden equations. I'm going to give you each a note card. I'm going to start out with this little gem. So, average velocity is equal to your change in position over your change in time. Would you all agree with that? You would say that that is true. Good. I'm glad that we can agree on things. If we're accelerating at a completely constant rate, we're not shifting gears, we're not doing anything, the rate of acceleration is constant, is it also true that our average velocity is equal to our initial velocity plus our final velocity divided by 2? Seem like a reasonable and true statement? Yeah, it is. It is. Well, what that means we can do, and this is what we're going to do a lot of today, is substitute that in for average velocity. So what we get next is VI plus VF over 2 equals delta x delta t. Why is this useful? Sometimes we actually want to know what initial or final velocity is. Sometimes we want to know what kind of distance it would take us to stop. If we've got this initial velocity and this final velocity, or how long it would take us to stop. So it's useful to have these things. We're going to do some algebraic magic. I'm going to do some Doseri magic here. Stick that up there. So we're going to factor out the 1/2. We get 1/2 quantity VI plus VF equals delta x over delta t. And then we're just going to solve this for delta x. And that's our first golden equation. So 1/2 VI plus VF times delta t equals delta x. And I have this really weird, I guess it's a bias. I'm going to rewrite that. I don't like the way I wrote that. When I line them all up on my golden equations card, I prefer that all of my solve fors be on that side. I don't know why. You don't have to be. You can be your own kind of weird. You don't have to be my kind of weird. So that's the first of our golden equations. I'll circle it in yellow. I would suggest putting that on your note card. That's number 1. Pardon?
All of it, or
Just what I circled. That's one of your goldens. My dream, and in the old building we started to approximate it, was that I was going to have a student artist paint this like really beautiful sort of golden parchment scroll kind of thing with like rays of light shining off it as if it was, some sort of divinely inspired document, and we were going to paint this beautiful thing on the wall, and then we would have the 4 golden equations. Well, I'm not allowed to paint on the walls in here. What we ended up doing was the last year in the old building, we just wrote the 4 golden equations in Sharpie marker on the wall. Didn't quite have the same panache. Page 53 in the physics book. Do you need to get physics books? Go get physics books. Okay. On page 53, there's a whole stack of problems. These are the 2C problems. Whole stack of problems using these equations. Let's see. I'll assign 3, 4, and 5. We'll get practice on these. I'm going to give you the worksheet packets for Chapter 2 tomorrow, which are slightly more complicated problems, but you get the answers. So, okay. Looking at, we'll do number 1 together rather than the example, because the examples are always kind of dumb. Okay, we have a car, and it accelerates uniformly from rest to a speed, we're told, of 23.7 kilometers per hour in 6.5 seconds. Delta t is 6.5 seconds. How far does it travel during this time? We don't know. So here are a couple things, and I haven't I haven't had this talk with you yet, but there comes a time when you have to have the writing things down talk. And as I said, most of you are just pretty smart critters. That's how you ended up in physics. You're good at math. In physics, more than anything else, I can tell you that the thing that will make your life easy is bookkeeping. And if you are naturally neat, well organized, and pay good attention to detail, you've got probably 30% of the battle out of the way. If you tend to not write stuff down and it's all kind of sloppy and it trails all over the place, you're going to be fighting yourself. The very first thing to do anytime you have a problem like this is list all your variables. And this is like seriously the gospel of list your variables. Write them down. So we're given delta t. What other information are we given?
Acceleration.
Are we? We're given speed. What speed? Is that an average velocity? Is it an initial velocity? Is it a final velocity?
Final.
It's a final velocity. This is a VF. So we have a VF of, well, what is the VF? Sorry, I should shut up. 23.7 kilometers per hour. Are we given any other velocities in this problem?
The rest, so 0.
Good girl. Yeah, VI, 0. Now, that's 0 kilometers per hour. That's 0 meters per second. The conversion for 0 is very easy. I'm going to go ahead and put it in meters per second because guess what? We have a conversion coming up because we were given a time in seconds and a velocity in kilometers per hour. So we will have to do a conversion. Okay, we have delta t, we have VF, we have VI. What are we being asked for? Delta x. So, you only have one of the golden equations so far. The golden equations all have 4 variables. Well, yeah, they do. They all have 4 variables. And we always have 3 of them. And we're always looking for that 4th one. So this is not 3-part algebra, this is 4-part algebra. We are looking for delta x. Now, this is nice because, of course, we only have one equation, and the only equation we have is delta x equals 1/2 VI plus VF delta t. Well, it couldn't be much easier because the very thing we're looking for is the very thing that the equation is already arranged to solve for. We don't have to rearrange anything, which is nice. As I said, the first thing to do is always list your variables. The second thing to do is always write down the equation that you're going to use. Right now, you only really have one. In short order, you're going to have 4, and you're going to be picking from that list of, oh, which one do I use? It was a skill I never mastered in physics, and boy, it would have saved me years of hassle. Okay, so plug it in. Oh, wait, we have to convert. Darn it. Do your conversion. So trick for converting this, despite the fact that I did that, do your hour down there. It really helps. Okay, so we've got, what, 0.6583 repeating times 10 to the first meters per second. And, you know, as was pointed out, this is not correct scientific notation. You would never leave an answer like this. This one's nice because, oh, that just means it's 6.583 repeating meters per second, and we can ditch the scientific notation. Okay, we have that. Good. Now what? When you are problem solving in physics, oh. Hey guys, push that back when you're done, huh? When you're problem solving in physics, I seriously give you a point for listing on a test. I give you a point for listing your variables. 1 stinking point. We get to the point where each problem is worth 10 or 15 points. Lots and lots of partial credit. I give you a point for writing down the correct equation. I also give you a point for showing that correct equation solved for the right thing. Now in this case you don't have to do anything. I also give you a point for plugging the numbers into the correct equation, because that's the stepwise fashion that allows you to show your process. Okay, so we're going to plug everything in. We've got a 0 meters per second. I like zeros, they're easy. 6.583 repeating meters per second. And I'm not writing out all the 3's here. You can just do a repeating sign. Sometimes I do my little dot, dot, dot afterward to indicate to myself that that number continues. What's nice about the calculators that we have is that you can store a number and go back and get it. Okay, so we've got 1/2 the quantity 0 plus 6.583 times 6.5. Save all those numbers. Don't round in the intermediate steps. It can change your number by a lot.
I got 21.5604.
Okay. And yours is off by about 1/3 of a meter because of rounding. So, which, I mean, you know, is insignificant here. When we get into much larger numbers, it becomes more significant. Okay, 21.39583 repeating meters. Okay. Do our units check out dimensionally? Now, obviously, we just derived this equation. We're pretty confident that it's rearranged correctly. We've got meters per second plus meters per second. That gives us meters per second times seconds. Seconds cancel out. We end up in meters. That's what we want. Okay. Quick review on Sig Figs. How many do we have? Fingers. You can be subtle. 2. Yeah. And right there's our limit. We had 23.7 with 3 sig figs, but we're limited by the sig figs here. So this is going to be 2 sig figs. Final answer for delta x is 21 meters. It's going to take 21 meters for this vehicle to stop.
Question. Are we limited by?
Can we find answers for these guys?
Guideline on scientific notation, if it's something that's, you know, going to be more than, if you're talking about more than 2 or 3 decimal places, it's probably easier to do the scientific notation. If it's 10 to the first, 10 to the negative first, 10 to the second, 10 to the negative second, I very often don't bother unless it has been easier for me to do the calculations in scientific notation. If that saved me a hassle, I'll do it. And I don't insist that you convert it into or out of. Scientific notation is a tool. Use it when it makes sense to use it. If I'm doing a conversion, I always use it because it's so much easier. But for final answers, you know, that's fine. It's the same number. Okay, this is easy. This is good, right? Okay, let's go on and derive the second. We would all agree to this, yes? Okay. We would all agree, I think, that delta V is equal to your VF minus your VI. Your change in velocity is equal to your final minus your initial. Your change in time, and this is one we use a lot less, is equal to your final time minus your initial time. We don't usually put in, you know, starting at 3.2 seconds and finishing at 7.8 seconds. We don't usually mess with that. Okay. Because of that, what we can do is take this and insert it. We're going to do a lot of this. So we say that acceleration is equal to VF minus VI over delta t. When is this useful? Well, what if we want to know how fast something's going at the end? How long is it going to take us to get to that final velocity? What rate of acceleration is required to get from velocity A to velocity B in such a time? So this one is generally arranged to solve for VF. So we're going to do that. First step to that would be A delta t equals VF minus VI. And then to finish the solve, we would say A delta t plus VI equals VF. And again, my stupid weird little bias about how I write these things.
Is this gonna go in the hole?
Yes, this is your, yeah, I should have circled that in gold. Ah, light comes off of it, angels sing, it sprouts wings. VF equals A delta t plus VI. This is one, for some reason I like this one because every time I look at it I think to myself, for me it helps if I can translate the equation into what it means in the literal world. That helps me a lot in physics because that's what physics is. Oh, yeah, how fast you end up going just equals how fast you were going to start with plus the rate at which you were accelerating and how long you had to accelerate. That makes perfect sense. Checks out dimensionally. There are some practice problems. That was a really easy one.
This is gonna be a part of the big, like, homework.
Yes.
The big
Yes.
homework.
The big homework. Yeah, for every chapter I just lump it all as one big chunk, and in physics it's typically some book problems and some, now we're starting to move into where we're going to have worksheets also. Okay, this one's a little bit uglier. This is sort of a nested derivation. Are we running out of time? I see people glancing at the clock. We're going to start this. So from the last slide, from what we just did, we can all agree on this now, conceptually, that how fast you end up going is equal to how fast you were going when you started, plus your rate of acceleration times the amount of time you had to accelerate. If we go back a little bit further, I think we satisfactorily proved that delta x is equal to 1/2 can't draw an I to save my life, VI plus VF times delta t. Could we agree to that? Okay, I'm glad. So, see this VF? You see this whole expression here that's equal to VF? Guess what? Exactly. I love these. And I love color-coded arrows because I find it really helpful. So we're going to take that expression for VF and we're going to jam it sideways into the other equation. You're going to need a shoehorn. Delta x equals 1/2 VI plus, I make liberal use of brackets here because they help me keep straight, oh that's VI, they help me keep straight what I'm doing. Close parentheses times delta t. Now we have some heavy-duty distribution to do here, obviously. Delta x equals, we're going to distribute, what should we distribute first? Well, we always start on the inside, right? So let's keep the outside left to its own devices. I'm going to move that delta t up here. If you didn't see how I did that, I put that there to simplify life a little bit. Okay, so now I'm going to start distributing this VI, and I get VI a delta t plus VI squared. And let's see, now I can distribute, is something wrong yet? Nope, nope, nope.
Aren't you adding?
Yeah, not multiple.
Oh, geez Louise. Okay, good. See? Excellent. So, hey, let's scrap everything I just said. Sorry. I apologize. Okay, well, let's get rid of that. I'm so glad that you guys are paying attention. Okay, scrap that. Delta x equals. So we're still going to move the 1/2 delta t up there. And we're going to go ahead and I'm just going to rewrite that for right now. A delta t plus VI there. Okay, so we can do some combining of terms. My apologies. Delta x equals 1/2 delta t. Well, VI plus VI gives us 2VI plus a delta t. So this is starting to look a little bit more manageable. Let's shrink a bunch of this stuff. Darn it. Let's move all of this. So now we do delta x equals, and we're going to distribute now. Well, 1/2 delta t times 2VI, we'll have some simplification, and 1/2 a delta t squared. So obviously our half and our 2 cancel one another out. This is traditionally written as delta x equals VI delta t plus 1/2 delta t squared. And that's the golden right there. Delta x vi delta t, oh, 1/2 a delta t squared. Geez, Louise, you got to keep an eye on me at all times, or I'll do something stupid. There. That's the third of your golden equations. You now have 3 out of 4.
Could you write that, the delta A, or A delta T squared divided by 2?
You could, this is really silly. My little brain is in such an engaged rut on this one that just the thought of it makes me go twitch, twitch, twitch. Yeah, you totally could. This is the form in which you will traditionally see it.
Are we going to be able to have this in a part?
Every single time you do anything in this class. If you would like to get them tattooed onto your forearm, that is fine with me. You will look really tough to, like, other nerds.
We'll be like, wow, they're probably really smart.
I got the 4 golden kinematics equations tattooed on my forearm because, you know. Okay, that's 3 of the 4. Let's do the 4th. Okay, so we've got those 2. We're going to do a couple things. We're going to get rid of this half because we're going to end up using this equation and we want to just have it rationalized. So if we multiply everything by 2, we get 2 delta x equals vi plus vf delta t. Okay. Well, we can rearrange that to solve for delta t, because it's very often convenient to have a measure for time. Especially when we start doing stuff on 2 axes, you want as many equations that involve time as possible and as many ways to approach time as possible, because time is what connects the entire world. It's a magical thing. So we're going to go ahead and solve this for t. So 2 delta x over the quantity vi plus vf equals delta t. Great. We've got an expression for delta t. We call this, and I'm really kind of anal about using correct math language. For me, it helps tremendously if I do it, see it, and hear the correct math language about it, and some of you may also be that way. It's like a trimodal thing with math. So we're building an expression here for delta t. Okay. And yes, I am cheating and looking at my old derivations because not all here yet. Well, I noticed something right off. We have an expression for delta t, and we have a delta t. So if we're in a situation where we have a displacement, we have initial and final velocities and acceleration, but we actually don't have delta t, this gives us a tool for getting those other variables when we don't know our time. So let's jam that in with a shoehorn. Vf equals vi plus a now times the quantity 2 delta x over vi plus vf. Oh goody. So we get vf equals vi plus 2a delta x over vi plus vf. Well, that's fairly hideous. But we have a simple solution. Let's shrink a few. We can start by moving this vi over. So we have vf minus vi equals 2a delta x over vi plus vf. Okay, let me just write the final, if you'd be so kind. We do some magic. We get average acceleration times 2 delta x is equal to vf squared minus vi squared. We'll finish it up. Actually, you know what? I'll do a video called the Golden Note Card. It'll be like a 3-second thing. Okay, 5 minutes. Watch it tonight. I'll post the problems. I will not be here tomorrow because I gotta go get stuff done. So that's it.